Sorry. Okay. So I'm Sharon Lapiner. I'm working in the Hebrew University. I'm a PhD student with Avishai Decker. And I'm going to talk about compaction and the relation to the blue nugget phase. Sorry, to black hole. This is the wrong title. Never mind. Okay, here it is. This is it. Okay. So black hole growth. So this one. Okay. So I'll start with describing compaction first. Mark talked about it on Tuesday, but I'm going to quickly go over it again. So we see here the sequence of events. This is the Villa simulation by Daniel Severino, very high resolution simulation. And starting from the left to the right, we see on the top row the gas. The first one is when you have a lot of gas in the galaxy. The second one is the compaction. All the gas is in the center. It's compactifying to the center. And post-compaction, the gas is depleted from the center. A disk is forming around it. And in the late stage, all the center is depleted from gas. You see a hole in the center and the ring forming outside, which is fresh gas coming from the streams. At this stage, the stars is basically, the core is the red nugget. And there's an envelope around it of stars. So, okay. So this is just a cartoon of the whole simulation, the basic behavior. So we look at the gas inside 1 kpc. We start with a diffused gas. Compaction, the gas is rising by a factor of 10. And quenching, depletion of the gas in the center. And now if we look at the star formation rate, it follows the same pattern. The stars are rising during the compaction phase, and then there's a plateau in the center of the galaxy, which means that there's a quenching in the center. So we find this if you just focus on the right panel. This is the virial mass versus time. And just to see that they all lie around the same scale, around the same mass scale. I won't go into it right now, but we think that basically below that, the supernova feedback is affecting the gas, preventing it from creating a major blue nugget. And above it, the hot CGM is preventing the entrance of fresh gas cold gas that will do this. But what I want to show you here is basically the relation to the black hole. And this is a simulation by Dubois et al. They simulate the same galaxy, once with supernova feedback and the other without supernova feedback. And you can see it in the red or yellow line. This is with no supernova feedback. The black hole growth on the y-axis is starting to grow almost immediately, very early times. And if you look at the black or gray line, you can see that with supernova feedback, until about redshift 3.5, the black hole is suppressed. The growth of the black hole is suppressed, and suddenly at some point it starts to grow. Okay, so in this case, at redshift 3.5, there's a merger. It's not a very big merger. I think it's 1 to 4. And if we look at the effective radius, we see this is the merger, and compaction happens afterwards. The galaxy is becoming small. The effective radius is decreasing. So below the critical mass, there's a strong supernova feedback, which will suppress the black hole growth. once the galaxy reaches certain mass, there's compaction, it overcomes the supernova feedback, and there's rapid black hole growth. This is another simulation showing similar behavior with supernova feedback, without supernova feedback, and you can see suppression of the black hole, and at certain mass, it starts to grow. This is work we are doing with the Johan now. This is using the New Horizons simulation with the high resolution, about 35 parsec maximum resolution. And we're doing, first of all, the same thing. The gas mass within 1 kpc is the blue line. So we see here compaction, and this is the black line is the black hole. This is the growth of the black hole following the compaction. And again, in another simulation, compaction followed by growth of the black hole. In the green line, you can see the distance of the black hole from the center. And we find correlation between the distance of the black hole and its growth, as well as from after compaction. What we are investigating right now, and it seems that once the compaction is building the potential well, the black hole can go to the center, as well as dragging it to the center with drag force from the gas. So, for example, in this galaxy,
17 hours.
So this is my computer. In this galaxy, the black hole came from outside. There's a merger going on, and then it's sinking to the center when there's compaction. So again, below the critical mass, this is the supernova phase. The winds from the supernova can evacuate the core, the black hole growth is suppressed, and the blue nugget formation is suppressed. Around the critical mass, there's a major compaction event. This is overcoming the supernova feedback. The potential well is built, and it can activate the rapid black hole growth. Above the critical mass, post-compaction, there's a hot CGM phase. Less gas can come in, but the recycled gas evacuated by the supernova feedback can come back and still feed the black hole. So this is from observations from candles. We see here the L shape of, this is on the y-axis is star formation rate, sort of star formation rate. On the x-axis is the compactness. So the compact blue nuggets appear on the quarter here below. And you can see the color is the value of the fraction of AGNs in each bin. So you can see very high fractions in this quarter. So the galaxies move in this way. This is from Foster Schreiber a few days ago, it came out. So I think Genzel showed the same yesterday. The fraction of the incident of black hole is correlated with the mass. So above a critical mass, there's a mass scale in which there's the incident of black holes is of AGNs is growing. And here, this is the effective radius. So as you go to more compact object, the incident of black hole is growing. And okay, so this is about the same thing. High mass value, in high masses, the incidence of AGNs is higher. And there is something in this direction. And going up on the main sequence, you can see some indications of higher values of AGN fractions. Oh, the blue nuggets are. Sorry. Okay. So this is what I showed before. These are the conclusions. That's it.
Thank you very much. Do you have questions for Sharon? Yes, please.
Have you made any effort to see what your black holes look like in the conventional scaling relations that we use at low redshift and also increasingly around Z of 1 to study black holes?
I don't have enough of them to see a real trend so far. Now I have a few more. I haven't analyzed them yet, but I plan to.
Can you start?
Yeah, sorry. So I'm curious. So there's already been a few observations done, like with Candle's data, for example, looking at AGN fractions as a function of galaxy morphology. And generally is that AGN fraction doesn't really care that much about whether a galaxy has bulge dominated or disk dominated. Does that still fit into this picture of wet compaction driving particularly strong AGN?
I think it's, okay, so we're looking basically at the major blue nugget. At this point, the bulge is created, but there are early compaction events which doesn't succeed, which doesn't make as a dramatic effect, but still you can see the AGN is active. So.
Okay, so you get activity at a range of bulge to disk ratios, in other words.
Yeah, you can still get it in I don't know.
Let's thank Sharon again. And next speaker is Sushmita